Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics playlist, we'll study magnetic dipole moment and understand what is similarity between current carrying area loop and bar magnet and how magnetic field of current loop is identical to electric field of electric dipole. We'll also understand significance of elemental level magnetic dipole moment in atoms to explain magnetic property of material and what is Bohr Magneton. Let's start. The concept of magnetic moment or magnetic dipole moment denoted by capital M is very important from our examination point of view. Magnetic field flux density of a current carrying circular coil at a very large axial distance can be obtained by this relation. For a coil of N turns carrying I current and radius A, if axial distance is very large compared to coil radius, in this summation A square plus X square, we can neglect small radius square A square and this become only X square, and with 3 by 2 power this become X cube, and this relation clearly indicate that axial magnetic field flux density of a circular current carrying coil is inverse of cube of axial distance. That means for very far away distance position from a current carrying loop, if distance is doubled, the magnetic field flux density become 1/8. Now this expression of magnetic field flux density or presentation of magnetic field by force lines of a current carrying circular loop or any other shaped loop or a bar magnet or even a electric dipole is quite identical, and in all those cases the respective field, in case of current loop and bar magnet, magnetic field, and in case of electric dipole, electric field, varies as proportional to 1 over x cube, and in all cases when the distance of observation position, which is very far away and large compared to their physical dimensions, that is separation between two magnetic pole or electric charges, then doubling distance of observation position will reduce field strength to 1/8. So just like the concept of magnetic dipole or electric dipole, we can generate magnetic dipole moment for a current carrying loop. Let's understand that. For a very far away axial distance position in comparison to coil radius, this expression of axial magnetic field flux density simplified as μ0 ni a square upon 2x cube or magnetic flux density become inverse proportional of cube of observation position distance. Now this mathematical expression can be compared with magnetic field flux density of a magnetic dipole of dipole moment m at an axial distance x, and that relation is μ0 upon 4 pi 2m over x cube. Both these relations are 1 over x cube proportional relation. Similarly, for an electric dipole moment, the axial electric field is given by 1 upon 4 pi epsilon 2p upon x cube. Now, magnetic field of magnetic dipole moment and electric field of electric dipole moment got a great similarity. This mu naught is magnetic permeability of medium, is a magnetic property of medium, and this epsilon naught permittivity of medium is electric property of medium. So for electric field we have used electric property, and for magnetic field calculation we have used magnetic field property. Now this M and P are respectively magnetic dipole moment and electric dipole moment, and both have similar type of 4 pi expression for rationalization of relation and a proportionality similar as of current carrying coil 1 over x cube. Now this expression of magnetic field flux density of a current loop on axis can be compared with magnetic field flux density of magnetic dipole moment. To produce 4 pi in denominator, we multiply it by 2 pi in denominator and numerator, and in denominator this 2 multiplied by 2 pi become 4 pi, and we got an expression μ0 upon 4 pi just similar to expression of magnetic field flux density by magnetic dipole moment. The x cube is same here, and the remaining terms, this pi with radius square become area of circular loop. This 2 with number of turns current and area of loop become 2 nia, and if you compare the two expression, then this magnetic dipole moment of a bar magnet and this product of turns current and area nia are just identical in position, and we can say for a current carrying loop this product of number of turns current and area nia is nothing but magnetic dipole moment. For a circular current carrying coil of radius r, this pi r square is area of current loop and product of number of turns current and area NIA is magnetic dipole moment, and magnetic dipole moment is a vector quantity and its direction is obtained by Maxwell right hand thumb rule, and this magnetic dipole moment is perpendicular to this current loop given by the direction of thumb if the finger of right hand are curled along the direction of current in loop periphery. This direction of magnetic dipole moment of a current carrying loop and axial magnetic field of a current carrying loop are just identical. So we can say for a current carrying coil or current carrying loop, the direction of magnetic dipole moment is same as the direction of axial magnetic field. Now this expression of magnetic dipole moment for a current carrying coil directly indicates that this magnetic dipole moment is equal to product of number of turns, current and area size of loop. So for a current carrying coil of constant current, magnetic dipole moment is directly proportional to its number of turns, and if we double number of turns in a coil with same area and same current, the magnetic dipole moment will get doubled. The magnetic dipole moment of a circular current loop depends upon radius square for same amount of current and number of turns, and if we double radius of circular current loop, its area will get 4 times and magnetic dipole moment also become 4 times. This expression clearly indicates that the magnitude of magnetic dipole moment depends upon area of current loop, the periphery of current enclose certain area, and that area size determine magnetic dipole moment, and it doesn't depend upon the shape of area. It may be circular, elliptical, square, pentagon, rectangle, triangle or hexagonal. Whatsoever the shape of current loop may be, for the same identical enclosed area and same amount of current and turns, the amount of magnetic dipole moment of all shaped current loop would be the same. For a multi-turn circular coil of constant current and fixed wire length, the length of one turn with radius r is 2 pi r, the circumference, and for n turn, the complete length become n times 2 pi r, and if this length is constant, then product of n and r, number of turns and radius, become constant, and in that case, the expression of magnetic dipole moment of current carrying loop Ni area is pi r square, can be converted in terms of constant nr by multiplication of n by both denominator and numerator. This n become n square and this become a constant square, that's a constant. So for same amount of current and same wire length, the proportional relation between magnetic dipole moment and number of turns become inverse relation, and if we double number of turns with same wire length, then the same current will produce half amount of magnetic dipole moment, and the reason is double turn got half radius and reduction of radius to half will reduce area to only 1/4. So double turns and 1/4 area will result in half amount of magnetic dipole moment. Now this relation of variation of magnetic dipole moment with respect to number of turns is different from variation of magnetic field flux density at the center of circular loop of constant wire length, and in that if we increase number of turns to 2 times, radius become half for constant wire length, and magnetic field flux density mu 0 Ni upon 2r at center of coil in coil plane become 4 times. Now in the same expression of magnetic dipole moment, if nr square is written as nr into r, then this n and r product for constant wire length is a constant. So magnetic dipole moment become directly proportional to radius, and if we make a coil of double radius with same wire length, its magnetic dipole moment will become double, as magnetic dipole moment is directly proportional to coil radius for constant wire length. So in examination with constant wire length, if variation of n is specified, we should convert this relation in this format, and if variation in coil radius is specified, then this relation nr square is made as nr multiplied by r to get the final proportional relation for constant wire length. If a single turn or same number of turn current loop is formed in different shape using fixed wire length, then for same peripheral length, the magnetic dipole moment for same amount of current depends upon surface area of current enclosed loop, and for given periphery, the enclosed area of circle having a regular polygon of infinite number of sides is the maximum. So a circular loop for same wire length and same amount of current will produce maximum amount of magnetic dipole moment, and a triangle with least 3 number of sides will have least area, so its magnetic dipole moment is least. So this is an increasing order of magnetic dipole moment corresponding to enclosed area for same peripheral length. Pentagon or hexagon got higher magnetic dipole moment compared to square but less than circle. Now this expression of magnetic dipole moment for fixed length of current loop and magnetic field flux density at center of regular polygon is just opposite to each other. For same wire length and same current, single turn triangular shape will produce maximum field flux density at center and circle produce the least magnetic field flux density at its center. Whereas for same wire length and same current, circle will have maximum magnetic dipole moment and triangle got least magnetic dipole moment. The concept of magnetic dipole moment is an elementary atomic level concept, and let's find out magnetic dipole moment of a revolving electron in an atom. In the Bohr atomic model, a negatively charged electron revolves around positively charged nucleus with a certain radius in a circular orbit with electrostatic attraction between nucleus and orbital electron producing centrifugal forces. Now in this circular motion of electron around nucleus, if time period of circular motion is t, then amount of current could be written as electron charge circulated in one cycle divided by time period of one cycle. Now for a circular orbit of r radius, this periphery is 2 pi r, and if linear velocity of electron in this circular motion is v, then time period can be written as peripheral length divided by velocity. And if we substitute the expression of t in terms of radius and velocity, we can express current of orbital electron as ev upon 2 pi r. If velocity is in meter per second and radius is in meter, then this expression of current is in ampere. This orbital motion of electron around nucleus become a single turn current loop, and for that magnetic dipole moment produced by this orbital electron is current into area, and in place of current we can write electronic charge peripheral orbital linear velocity divided by peripheral length 2 pi r, and when we simplify this become EVR by 2. Now electron being a negative charge, the current direction is just reverse of negative charge movement direction, and as per Maxwell right hand thumb rule, the direction of axial magnetic field or magnetic dipole moment for this current loop is given by thumb of right hand perpendicular to this plane if the curl of finger matches with the direction of current in loop. Now in place of negative charge, as it is in atoms, if this revolving charge is a positive charge, then the direction of motion of positive charge and direction of current becomes identical, and in that case the curl of right hand finger and the direction of motion of positive charge will have same orientation, and thumb will give the direction of magnetic dipole moment. The expression of magnetic dipole moment of orbital electron EV r upon 2, E is electronic charge, V is peripheral velocity, and r is a radius of circular orbit, can be converted in terms of angular momentum of orbital electron by multiplication of mass of electron to both numerator and denominator, and this expression now can be simplified as E by 2 me. E is charge and me is mass of electron, and this expression mass, velocity and radius mvr become angular momentum of orbital electron in atom, and that is denoted by capital L. And if we use vector format, then we can say magnetic dipole moment of an orbital circular moving charge is directly proportional to its angular momentum. Higher the angular momentum, higher would be the magnetic dipole moment, and both would be in the same direction for positive charge, and for this electron like negative charge, the direction of angular momentum and magnetic dipole moment are opposite to each other, and this negative sign indicates that relationship of direction between magnetic dipole moment and angular momentum. So we can say magnetic dipole moment of an orbital charge directly proportional to angular momentum is EL by 2 me. To explain magnetic properties of different materials, Ampere had given a very bold hypothesis that in material, atomic level magnetic moments exist, and to explain hydrogen-like atom, when Bohr hypothesis told that there are some stationary orbits in atoms where angular momentum become an integer multiple of h upon 2 pi, and it is quantized, then this approach or Bohr hypothetical relation of angular momentum of orbital electron can be used to find out magnetic dipole moment of an electron in Bohr-like atom, and this elementary magnetic dipole moment is known as Bohr Magneton, and it use discreteness or Bohr quantization condition as angular momentum of orbital electron is integer multiple of h upon 2 pi, where h is Planck's constant, a constant used by Max Planck to explain energy of photon in radiation, and this n is a integer natural number 1, 2, 3, etc., indicating number of Bohr orbital, and later on this become our principal quantum number 2, and now this expression can be simplified as Bohr magneton is n times Eh upon 4 pi m, and this clearly indicate that there exists a elementary minimum size of magnetic dipole moment Eh upon 4 pi me, that is called Bohr magneton, and all other magnetic dipole moment are integer multiple of that only. So this Eh upon 4 pi me is a quantum of magnetic dipole moment, and here electronic charge and mass ratio is called as specific charge, and it got a value 10 to the power 11, and in MKS unit Planck constant is 6.626 into 10 to the power minus 34 joule into second. So Bohr magneton can be calculated by using value of electronic charge, Planck constant, and mass of electron. As per Bohr hypothesis, magnetic dipole moment of orbital electron in nth orbit is n times Eh upon 4 pi me, and for elementary minimum dipole moment we can substitute minimum value of n in first orbit, n equal to 1, and when we substitute n equal to 1, the elementary minimum magnetic dipole moment comes of the order of 10 to the power minus 23, and unit is current into area, ampere meter square. So this 0.927 into 10 to the power minus 23 ampere meter square is minimum possible magnetic dipole moment of our world, and it is called Bohr magneton, and all other magnetic dipole effects are produced by summation or integration of these elementary magnetic dipole moment. Now in an orbit, beside orbital motion of electron around nucleus, electron also spin around its own axis, and the spinning charge also have associated spinning angular momentum, and proportional to angular momentum that spinning electron also possess magnetic dipole moment, and our later studies clearly indicate that in three-dimensional random symmetrical distribution of orbital motion, the orbital magnetic dipole moment vector summation become almost negligible, but the spin of electron in all orbital positions produce spinning magnetic moment in the same direction, and when spin get compensated, that magnetic dipole moment also get cancelled out. But if atoms like iron, nickel, cobalt have considerable number of unpaired spinning electron, and due to mutual cooperation in material, if domain formations takes place, then those material could have a considerable amount of magnetic dipole moment, and that results in magnetic properties of these ferromagnetic materials. So in our other chapter, we will study the magnetic behavior of all non-magnetic and magnetic dia, para, and ferromagnetic material on this concept of Bohr magneton. We hope this learning video has explained each and every part of magnetic dipole moment, which usually least talked and explained in our academic world, but asked frequently in all examinations. Our other learning video are also equally useful in exam preparation. You can use them in your studies and share them with your friends. And if you need our online doubt clearing classes support and dedicated exam centric notes, do join our YouTube membership by pressing join button just beneath. Happy learning. Thank you very much.